Students. So today we talk about continuity equation. Now this equation is one of the basic equation of fluid kinematics. Now this equation is one of the basic equation of fluid kinematics. So in our syllabus we have three form of continuity equation. One is the general form, second is the Cartesian form, and third is the polar form. So we have three forms of continuity equation in our syllabus. So I first try to derive the general form of continuity equation. So for that I consider one pipe of varying cross section. Now say we have this pipe, its cross section is varying. This is its central axis. Okay, so this is section 1 and this is section 2. So I have a pipe now. Now at section 1, say capital A be the cross sectional area, V be the velocity of flow, and rho be the density of flow, and this is the flow direction. So here this is the flow direction. So at section 2, we have cross sectional area A plus dA, velocity V plus dV, and density say rho plus d rho. Okay, so A is for cross sectional area, V is for velocity, and rho is the density or mass density, you can say. Now here V is the uniform velocity. V stands for uniform velocity. So in last class, I already explained to you the meaning of uniform velocity. So here at section 1, V is the uniform velocity, and at section 2, V plus dV is the uniform velocity. Okay, so now I try to write the mass of flow, the mass flow entering through section 1. Okay, in a time interval of dt. So a very small time interval. I try to write what is the mass flow or what is the mass entering through section 1. Now mass entry, I write it as, now mass as you know, I write it as volume multiplied by density. Now volume I can write as volume of liquid or a fluid which is entering through section 1. So that volume I write it as cross sectional area at section 1 multiplied by the distance of fluid moved in time dt. Okay, so if I say initially the fluid is over here, after time dt the fluid moves to this distance. So this movement is in time dt. So if I try to write this distance, so that distance I write it as velocity multiplied by time. So A multiplied by V dt gives us the volume. So now I can write the mass entry through section 1 is equal to A V dt into rho. So that is equal to A V rho into dt. Similarly, I write the mass outflows through section 2. So that mass outflows we can write it as on the same line. The cross sectional area at section 2 is A plus dA. Volume is V plus dV. Density is rho plus d rho multiplied by time dt. Okay. So now I try to write next the mass accumulated. The mass accumulated between the two sections. That is section 1 and section 2 in time dt. So that we can write as dm. So that is equal to mass entry minus the mass outflows. So mass entry is a v rho dt minus the mass outflows as a plus dA into v plus dv into rho plus d rho into dt. Then we can write as dm upon dt, take dt on other side, is equal to, now here you see you have one term as a v rho dt with negative sign. So that cancels with this term. Okay. So now you can write it as, so a v rho dt cancels with a v rho dt, and the remaining terms we have minus the product of a v into d rho. One term is a v d rho, another term is v rho dA, the third term is a rho, okay, and dv. Now the remaining terms having either the product of dA into dv, or the product of dv into d rho, or the product of dA into d rho. So these all are the small quantities and we can neglect them. Very small quantities, we can neglect them. So now we have this relation. Now further, in case of steady flow, in case of steady flow, as we already studied, that in case of steady flow, the mass flow rate is constant. Mass flow rate is constant. So therefore, dm by dt we can write as 0 for steady flow. So therefore, we again write this equation as a v d rho plus v rho dA plus a rho dv equal to 0. Now we divide all these terms by term rho av. We divide all these terms by rho av. So now we have the first term as d rho by rho plus dA by A plus dV by V equal to 0. So further we can write it as d of rho av equal to 0, or you can say rho av is constant. Now what is the meaning of this relation? Now this is the general form of continuity equation. Now the meaning of this relation is the mass of fluid flow per unit time through any section is constant. So rho av is mass flow rate. The term rho av that we call as mass flow rate. Now you see its units also. For rho we have kg per meter cube, into area is meter square, into the volume is meter cube. So v is velocity, not volume, it is velocity. So v is velocity. Now the unit for v is meter per second. Okay, so you can see meter cube cancels with meter cube. So unit for rho ab becomes kg per second. So therefore it represents, the term rho av represents the mass flow rate. Okay, so the mass flow rate is constant along any section. That is the general form, that is the continuity equation. Okay, now this equation holds, good for compressible as well as for incompressible fluids. Okay, so for compressible fluids you can write as rho 1 a1 v1 equal to rho 2 a2 v2. This is for compressible fluids. Okay, now in case of incompressible fluids, there is no change in density when we move from one section to another section. So therefore rho 1 is equal to rho 2. So you can write this relation as a1 v1 is equal to a2 v2. Now you see the units for a1 v1 or a into v. The unit for area is meter square and for velocity is meter per second. So this unit becomes meter cube per second. So the term AV represents volume flow rate. This term represents the volume flow rate, and we call it as Q, that is discharge. So volume flow rate is discharge. So now you can say for incompressible fluid, discharge remains constant. Okay, that is the continuity equation. So from this relation, now you can write as AV is constant for incompressible fluid, or you can say Q is constant for incompressible fluids. Okay, from section 1 to section 2 along the pipe, the discharge remains same. Okay, so this is the general form of continuity equation. So this one for compressible fluid and this one for incompressible fluid. Okay, now next I try to derive the Cartesian form or the differential form of continuity equation. Now this is also same as the Cartesian form, means we try to derive the continuity equation along x, y and z coordinates. Okay, so for this we consider a block type element. Now say we have this a block type element. This is a block type fluid element. We have three axes. Okay, so this is x-axis, this is y-axis, and this is z-axis. Now say this element has distance dx along x-axis, dy along y-axis, and dz along z-axis. Now say along face this one. Okay, so I mark here the two phases. These are the two phases of this block. So along x-axis, I say the velocity is u, that is the entry velocity, and the leaving velocity along x-axis is u plus curly u by curly x dx. Means there is some change in velocity along x direction with respect to x. So that we can represent as, mathematically represented as curly u by curly x into dx. Okay. So now I try to write the mass entry, the mass entering along x-axis. So if I mark the faces, so say this is A, this is B, this is C, this is D, and in back you have E, F, this is G, and this is H. So mass is entering through face AD, HE. Okay, so this mass entry we can write it as density multiplied by volume into area in time dt. So that is rho AV into dt. So density we can write as rho, sorry, not volume, this is velocity. So again you correct here, this is velocity, rho AV. Okay, this is velocity. Okay, so rho A into V into dt. So here V is velocity. Now here mass entry we find along x-axis. So we write it this V as U. We can write this V as U, or you can write it as rho U A dt. This is the mass entering the face AD HE, or you can say along x-axis. Okay. Now similarly, you can write the mass outflows. So mass outflows, you can write that is from face BFGC. Okay. So that is equal to, now say when mass outflows, there is change in the product rho and U. Okay. Density changes as well as U changes, and this change takes place along x direction. So you can say there is some increment in rho U in the product of rho U along x direction. So that we can write as rho U plus curly by curly x of rho U into dx multiplied by area. Now area of the entering face. that we can write as dy into dz. This is dz. Okay. So area is dy into dz into time is dt. So this is mass outflows. Now you can write the mass accumulated. Mass accumulated in time interval of dt along x direction. So this mass accumulated you can write as mass entry minus the mass leaving. So mass entry is rho u, this term, rho u. A area you can replace by dy into dz into dt minus this term, rho u plus curly by curly x of rho u dx into dy dz into dt. Okay, so rho u dy dz dt you can cancel with this term. So now we left with minus curly by curly x of rho u into dx dy dz into dt. Okay, so this is equation number 1. So this is our mass accumulated along x direction. Now similarly you can write the mass accumulated along y axis as well as along z axis. So along y axis the mass accumulated is minus curly by curly y of rho v. Now let us say v is the component of velocity along y axis. So this is velocity v. Along here this velocity is v. So here along y direction the velocity is v plus curly v by curly y into dy. Okay, so it is curly minus of curly by curly y into rho v into dx dy dz into dt. Equation number 2. Similarly along z axis it is curly by curly z of rho w dx dy dz into dt. Equation number 3. So w is on back face you have velocity w and on front face you have velocity w plus curly w by curly z into dz. Okay, so now you can write the total mass accumulated in time dt. So that is sum of equation 1 plus 2 plus 3. Okay, so that is equal to minus curly by curly x of rho u curly by curly y of rho v curly by curly z of rho w into dx dy dz into dt. Okay, now say this is equation number 4 now. Okay, now let us say in this particular element now the mass entering is m. Okay, now after time dt the mass leaving is m plus curly m upon curly t into dt. Now the variation in m with respect to time. So mass entering is m. Okay, and after time dt say the mass leaving is m plus curly m by curly t into dt. Okay, so now by this you can write the mass accumulated again. So that is the mass accumulated. You can write it as mass leaving minus the mass entering. So now I write again the mass accumulated in time dt. So that is equal to m plus curly m by curly t into dt minus the mass entry. So it is curly m upon curly t into dt. Okay, so curly by curly t. Now m you can write as mass. So mass is the density into the volume of fluid into dt. Okay, so this comes out to be curly rho by curly t into, now the volume of this element is, the volume of this block is dx dy dz, the product of dx dy into dz, then this dt. This is your question number 5. Now question 4 is your mass accumulated in time dt. Equation 5 is again mass accumulated in time dt. So now I equate equation 4 with equation 5 because both are the mass accumulated in time dt. So therefore, I equate equation number 5 with equation number 4, that is as. So equation number 4 is with negative sign curly by curly x. This is your equation number 4. Rho u plus curly by curly y rho v curly by curly z rho w into dx dy dz into dt equal to curly rho by curly t dx dy dz, that is your equation number 5 into dt. Now you see this term cancels with this term. So now we left with curly rho by curly t, then you rearrange the terms also, plus curly by curly x of rho u plus curly by curly y of rho v curly by curly z of rho w equal to 0. Okay. Now this is the differential form, the required differential form of continuity equation. Okay. Or you can say this is the Cartesian form of continuity equation. And we can use this equation for three-dimensional flow because it involves x, y, and z variables. Okay. So you can say this is the continuity equation which we can use for three-dimensional flow. Okay. Either it may be steady or unsteady. Okay. Or it may be compressible or incompressible. So for all these conditions, this equation holds good. Okay. Now if I use one assumption over here, now say the flow is steady flow. If the flow is steady flow, you can write dm by dt equal to 0. The mass flow rate is constant. Okay. So when mass flow rate is constant, that means the change in density with respect to time is also constant. So you can also write for this as curly rho by curly t is also equal to 0. So now you can say there is no variation of density with respect to time. Okay, no variation of density with respect to time, that is for steady flow. Okay, so for steady flow, this term is 0. So now you left with curly by curly x rho u plus curly by curly y rho v plus curly by curly z rho w equal to 0. So this is the equation for steady flow. Now if I put one more assumption, now say the flow is incompressible also. Now if flow is incompressible, so that means there is no variation of density with respect to distance also. Okay, so from this equation, you can write rho curly u by curly x plus u curly rho by curly x. Okay, the first term. Similarly, rho curly v by curly y plus v curly rho by curly y. Okay, similarly, the third equation w curly rho by curly z plus rho. Okay, I write with rho first. Okay, so this term I write as rho curly w by curly z plus w curly rho by curly z equal to 0. Okay. Now I combine the density terms in one bracket and remaining terms in another bracket. So now I try to combine these three terms and try to combine these three terms. Okay. So now I can write. So velocity term first, u curly rho by curly x plus v curly rho by curly y plus w curly rho by curly z. Okay. Plus rho outside within bracket you have curly u by curly x curly v by curly y curly w by curly z equal to 0. So if flow is incompressible, so this term is 0, this term is 0, this term is 0. Okay, so we left with only this part. So this is the product. So again, rho becomes 0. So now we have a simple equation, curly u by curly x, curly v by curly y, curly w by curly z equal to 0. So this is the three-dimensional form of continuity equation for steady and incompressible flow. Okay, so this is the three-dimensional form of continuity equation for steady and incompressible flow. Okay, so this is all about the Cartesian form or the differential form of continuity equation. Okay, now the next is